In this problem, we have a disco ball, so that's a hollow sphere, being accelerated by a small electric motor with 40 watts of power for 2 seconds. And I want to get a couple things done before I start to answer all the questions here. First off, we have the power and the amount of time that it acted for. So just as a reminder here, power is the amount of energy transferred divided by the amount of time it took. So it's a rate of energy transfer. The units of power are going to be joules per second. And I can see that if I turn this around and say delta E equals P delta T, all I have to do is multiply power by time to get the total energy delivered. So in this case, it's going to be 40 watts, which are joules per second, multiplied by 2 seconds, and I get 80 joules of energy. Second, before we get started, I want to apply this moment of inertia formula for a hollow sphere. And the moment of inertia is 2/3 mr squared. So let's get I first. 2/3 mr squared. And that's 2/3 times the mass, which was 1.5 kilograms, times the radius. It needs to be in SI units, so I already converted it to meters. It's 0.25 meters all squared. And when I run the numbers on that, I get 0.0625 kilogram meters squared. All right, now we're ready to start with the official questions. Part A, compute the final angular velocity of the ball. Well, I know how much energy was pumped into it. So I can look at my rotational kinetic energy formula. K rotational is going to be 1/2 I omega squared. And I see pretty quickly here that I can solve for omega by multiplying by 2, dividing by I, and square rooting. So omega is going to be 2 times the rotational kinetic energy divided by I square rooted. I plug in my numbers, and the rotational energy of this thing is the 80 joules given to it by that electric motor. So I have 80 joules. And then divided by the moment of inertia, 0.0625 kilogram meters squared. So when I crunch the numbers on this, I get 50.6 radians per second. Moving on to part B, compute the angular displacement during this 2-second period. One way to handle it is with our first kinematics equation, but that one has an angular acceleration in it, and I don't have that yet. Now, you could compute it, and in fact, we're asked to in part D, but I wanted to just show how to do this without knowing the angular acceleration in part B. So I have theta minus theta naught. This is what I listed in another video as the fourth angular kinematics formula. Provided alpha is constant, this is true. And it's just something we're assuming in this problem. You can take the arithmetic mean of the angular velocities in the initial and final moments. That's their sum divided by 2 and multiply by the amount of time, and you're going to get this displacement. That's a delta theta, or an angular displacement. So my initial was 0 because we accelerated from rest. So I'm not going to write that. The final is 50.6 radians per second divided by 2 seconds, multiplied by how much time went by. So just coincidentally in this problem, that's also a 2, and these cancel. And I get 50.6 radians for the angular displacement. The tangential speed at the equator. Okay, so we're asked for the speed right along here. And the reason I had to specify that is you have to know how far this point is from the rotation axis. Well, if you're on the equator, then your distance to the rotation axis is exactly 1 radius. And we just used the formula V equals R omega for this. And the radius is 0.25 meters. And omega is something we already computed, 50.6 radians per second. And I end up with a tangential speed at the equator of 12.6 meters per second. Part D, compute the angular acceleration at the equator. Okay, I can do this by just saying, and technically we're talking about an average angular acceleration here, but if I tell you the angular acceleration is constant, then that's equal to the average value. I have delta omega over delta t, and final angular velocity was 50.6, initial was 0, delta t was 2, and I end up with 25.3 radians per second squared. And finally, in part E, I want to know at t equals 1 second, so halfway through the process, what's the centripetal acceleration and the total acceleration at the equator? So at t equals 1.0 seconds, I need to find out how fast this thing is rotating, and I'm going to do that with an angular velocity is what I mean. So omega equals omega naught plus alpha t. It was initially at rest. So my angular velocity omega is going to be 25.3 radians per second squared times 1.0 seconds. And that gives me 25.3 radians per second. Okay, then the centripetal acceleration could be given by r omega squared. You could also say v squared over r, that old formula from earlier in the course. But then I would have to use this v up here, which in practice sometimes causes more calculation. So when we're doing angular kinematics and dynamics, I like to use the r omega squared version. And r is 0.25. Omega is 25.3. And I'm going to square that. And when I compute the centripetal acceleration, I get 160 meters per second squared. Then I look at the tangential acceleration, because I'm trying to get the total acceleration here. And the tangential acceleration is just r alpha, 0.25 times 25.3. And that gives me 6.33 meters per second squared. The total acceleration is the vector sum of that tangential piece and the centripetal piece, which point perpendicular to each other. So I'm going to pop in a little picture just to remind you what this looks like. So I had to just kind of pop it in there between parts D and E and obliterated some of my units, but hopefully that doesn't cause any issues. And I wanted to look at, just for some point on this circular path, this is kind of a view from above the North Pole of the disco ball, and we're looking down at the equator, which is now on the edge. There's my tangential acceleration, so pointing tangent to the trajectory, and then I have a centripetal acceleration pointing to the center of curvature. These two things are perpendicular, and that means when you vector add them and get their magnitude, you're just using the Pythagorean theorem for that. So my calculation here for A total is the square root of AC squared plus A tan squared. And this will be dominated by the larger term because the centripetal acceleration is so much bigger. And I get square root 160 squared plus 6.33 squared. And it comes out to actually 160.1 meters per second squared. So the addition of that little tangential acceleration component only changed it by a 0.1 compared to that centripetal, just because the centripetal was so large.